Hello everyone, good evening. Okay, so welcome to our second lecture, all right, on this module. Okay, so we have about 21 of you in, 20 of you in, all right, yeah. So let me get started, okay? So those who are probably not yet in might probably join in a while, all right? So let me get started and we can continue from where we left off. Okay, can you all see my screen here? Yes. Okay. Okay. Thank you. All right. All right. So for today, basically, we are going to continue with where we left off, which is from the number systems. All right. So we're going to finish up this chapter. All right. Which we still have the concept of the negative numbers, which we're going to discuss today. And after that, we're going to go on to MIPS. Okay, so I'll talk a bit more on the MIPS, okay, when we come to that, all right, but that is a huge chunk by itself, all right, which will cover a few weeks, all right. Yeah, so I've also released the first tutorial, okay, which we will go through next week, all right. So the first tutorial will be on the number systems and some C programming, all right. So it's just to recap on the programming techniques as well as look at this number systems that we are covering in this topic. Okay, so that tutorial one has been uploaded. All right, so you can go ahead to try it. All right, so next class we will start off with the tutorial first, and then it will go on to the lecture. Okay, so last lesson we stopped at this, the ASCII table. All right, so we were discussing and we saw that the ASCII table is basically a way in which you can transmit characters across systems in a standardized way. All right, so again, there are many different types of tables or codes or systems to enable us to transmit data from one device to another device. So ASCII table is one of the ones that was used when the keyboard came along. All right, so it is a 7-bit code. All right, and I think what the key takeaway that we looked at was the interpretation of data. All right, so if you remember this example that we discussed, all right, we saw that when I declare a variable, okay, like this, okay, num, okay, I put a value of 65. All right, at the same time, even though the value is 65, what does it mean? It means that the ones and zeros occupy a value of 65. All right, and what is 65? All right, so let me go back to our calculator here. Okay, so if you look at the conversion, 65 is this 0 1 0 0 0 0 0 1. Okay, 0 1 0 0 0 0 0 1. Okay, so 0 1 0 0 0 0 0 1. Okay, so in terms of translating this, okay, we can come back here. Okay, so 0 1 1 0 0. So the first 3 bits is this, all right, which is so we need to look at the lower 7 bits. Okay, so it's 1 0 0 and 0 0 0 1. Okay, so 1 0 0 and 0 0 0 1 is this and this. So that points to A. Okay, so when I use my program and I say I want to interpret this binary value, this 8-bit binary value, okay, as a decimal, okay, as I specify it as a format specifier as decimal %d, I actually print out the actual value 65. Okay, but at the same time, when I use the format specifier as %c, that means I want to take this same 8-bit value but interpret it as an ASCII character, okay, by putting it as %c, and when that happens, it prints out as uppercase A. Okay, so the key thing is for both of this, all right, the actual value is the same. The actual ones and zeros is the same. All right, but because we are interpreting it differently for the two different printf, we get two different output. Okay, so that is, I think, the key takeaway that we must always understand, that whenever we declare variables in the code, all right, we have an intention, correct? So it's in our mind that, okay, I create this variable, it is supposed to hold this value, it is supposed to hold this information for me, all right? But exactly how we interpret that information, only the programmer knows, all right? So as far as the computer is concerned, it is still the same ones and zeros, but how we interpret it is in the mind of the programmer, all right? So that is always important. Okay, so that is where we had we stopped last week. So this was a past year exam question. All right. Again, this doesn't actually apply to you because we don't use Sunfire and we're not going fully into C programming. Okay, in this module. All right, but this was from the full-time module, the CS2100. So for that, they use Sunfire to run their C code. Okay, so when you run this, okay, on Sunfire, okay, what is the expected output? So in this case, we say that we have a variable n, and this is initialized to this value. And I run a loop 10 times, and in each iteration, I increment it by 1. Okay, so what would be the output after it runs this loop? Okay, so since the last ending is 40, after I run 10 times, will it be 50? Okay, so that is a question. So we will come back to this later on, okay, another slide. Now let's again that the answer to that actually lies in understanding this concept, which is negative numbers. All right, so until now, okay, we have mostly looked at the interpretation of binary and everything as positive numbers. Okay, so how do we represent, okay, negative numbers in the computing system? So there are three sort of techniques that have been developed over time. Okay, the one that we should probably focus on is this 2's complement. Okay, but we are going to just look at the other two just to understand. So why 2's complement is because that is the default system in all computing platforms. Okay, if you take up your handphone, even the calculator on your laptop, everything uses this 2's complement system. Okay, now how do we look at it? So the first technique is the sine and magnitude. So the sine and magnitude basically is a very simple, straightforward technique where they dedicate a single bit to represent the sign. Okay, so if the most significant bit is 0, then we say it's a positive number. If the most significant bit is 1, we say it is a negative number. All right, so what we are doing is we are taking one bit and reserving that one bit to represent the sign. Okay, so whatever binary bit stream I have, I isolate, okay, the most significant bit, and if the most significant bit is 0, that means it is a plus. Then I just convert the remaining bits to the actual value. Okay, similarly over here, the most significant bit is 1, then 1 translates to negative. So it's a very easy and straightforward way, all right, to represent positive and negative numbers. Okay, so of course, this is what you get. You have the largest value and the smallest value. All right. So that is a sine and magnitude technique. All right. So in order to create the negative representation, all you need to do is to keep the lower bits. Okay, and all you need to do is invert the sign bit, which is the most significant bit. All right, so you don't need to change anything else. So you just keep everything else as it is. And if it is positive, the most significant bit is 0. If it's negative, the most significant bit is 1. Okay, so it's a very straightforward technique. Okay, the next technique is what you call the 1's complement. All right, so the 1's complement is basically, so this is of course the sort of mathematical way to derive it. All right, but the easiest way to look at it is just basically you flip all the bits. Okay, flip all the bits. So for example, okay, if I would take any number and I want to represent the negative, I just invert all the bits or flip all the bits. Okay, so now let's take this example. So this 00001100. So this is actually 12. All right. So if you want to confirm it, you can just key in your calculator. So you can see that the decimal value 12 as a representation of 1100. So these are the lower 4 bits. Okay, so 12 is represented as 1100. Okay, so again, if I say it's an 8-bit value, then I just put 4 zeros in front of it. Okay, now this is positive 12. If I want negative 12, all I need to do is I flip all the bits. So the 0 become 1 and the 1s become 0. All right, so that becomes your negative 12. So it's an easy way to represent the positive and the negative by just flipping the bits. Okay, so that is the ones complement technique. All right, so in the ones complement technique, okay, the most significant bit is still representing the positive and negative. So the moment I look at the most significant bit, okay, I can still straight away say that if the most significant bit is 0, then it is a positive number. If the most significant bit is 1, then I say it is a negative number. All right, so the most significant bit can still help us to immediately tell whether it is a positive or negative number. All right, so given any number, okay, if I want to take the ones complement, what I need to do is I first need to find out what is the actual representation of it. So if I look at this negative 80, all right, so the first thing you want to do is you want to know what is the actual representation of 80. Okay, so the actual representation of decimal 80 is this. So 0101 0000. Okay, 0101 0000. So this will be negative 0101 0000. Okay, so this is the actual value, which is positive 80. But what I want is negative 80. So in terms of ones complement, all I need to do is I flip all the bits. So it will become 10 10 11 11. Okay, 10 10 11 11. So that is now negative 80. All right. So again, what we need to do is we need to make sure we look at the most significant bit to know whether it's a positive or a negative number. All right. So the twos complement, all right, is just a simple extension from the ones complement. All you need to do is you need to do the flip. Okay. All bits. Okay, and then you plus 1. So this is the only additional thing you need to do. You need to do a plus 1 after that. All right. So let's look at it in the same way. So 12 is given as this binary stream over here. Okay, so let me write it over here 0 0 0 0 1 1 0 0. And then I need to add with, so first thing I need to do is I need to flip. I need to flip the bit. So it become 1 1 1 1 0 0 1 1. Okay, and after that I need to add a 1. Okay, so this is bit addition. Okay, so I'm not sure if you know how to do this. So in terms of bitwise addition, okay, the rules are simple. Okay, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is also 1. 1 plus 1 is 0 carry 1. Okay, 0 carry 1. So it's the same way in which okay, the same way in which you do like your normal carry. Okay, so there's a question to explain the formula, right? So basically this formula here is the way to derive the answer. Okay, so basically what it says is, okay, if I want the 2's complement of a number, I can use this formula. Okay, this formula is the same as using this technique. Okay, so let me explain how the formula one works. So for this, basically what you need to do is you take 2 to the power of n minus x to find negative x. Okay, so how does that work? Now, let's take this same number. This is an 8-bit number. So if it's an 8-bit number, n is 8. So it become 2 to the power of 8. Okay, so this n is the number of bits. So in this case, 8-bit. Okay, and if I want to find negative 12, okay, what I want to find is negative 12. So I must take 2 to the power 8 minus x, which is minus 12. All right. So what is 2 to the power 8? Okay, so 2 to the power 8 is 256. Okay, so let me just show you here. Two power 8. Okay, it's 256. So what we have is 256 minus 12. So 256 minus 12 is 244. Okay, so when I compute this to the power 8 minus 12, I get 244. Now, if I take 244 and I convert it back to binary, okay, I will get this answer, which is the value for negative 12. Okay, give me a minute. Okay, so that gives us that gives us the answer. All right, 244, and 244 is actually negative 12. Okay, so let me show you how that works here. Okay, so this gives me 244, and 244, okay, in the binary representation is this. All right, and that is actually negative 12 in 2's complement. Now, if I do the flip plus 1, I'll get the same answer. Okay, if I follow this addition rules over here. So let's follow these addition rules. So now what you're going to do is this, correct? 1 1 1 1 0 0 1 1 plus 1. So 1 plus 1. Okay, so 1 plus 1 is 0 carry 1. And again, 1 plus 1 is 0 carry 1. 1 plus 0 is 1. So 0, there's nothing here. So 0. So the rest is all just zeros. That means there's no change. All right. So if you look at this answer and you look at this answer, it's the same. Okay. So basically, you can use whichever technique you want. Both are the same. All right. So if you prefer to use the formula, you can go ahead and use it. If you just want to do the flip plus 1, is also fine. Okay. Either way is fine. Okay. As long as you know that this is how you compute the 2's complement. All right. So that is the basic idea. And as before, you can always look at the most significant bit to know whether it is positive or negative. Okay, 0 means positive, 1 means negative. Okay, now let's look at this again, the same thing. Okay, so 80, all right, if you convert, okay, it's the same thing. Okay, there's a calculator. Okay, so 80 is given as this. Okay, 0 1 0 1 0 0 0 0. Okay, so let's go ahead and do it. So 0 1 0 1 0 0 0 0. So the first step is I flip, so I get 1 0 1 0 1 1 1 1, and after I flip, I add 1. Okay, so 1 plus 1 is 0 carry 1. 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 1 plus 0 is 1, then 1 and 0 and 1. So this is the 2's complement. And if you look back at the calculator now, okay, this is the 80. Now if I put a negative in front of it, so if I change the sign to negative, okay, what you will observe? You will observe that the answer here is the same. All right. Okay. You will notice that, of course, it has a lot of ones in front. All right. So that is because you are dealing with a 64-bit system. So all the answers will be represented in either 64-bit or 32-bit. Okay, depending on the app that you're using. Okay, or the system you're using. All right. But if you look at the lower 8 bits, they are the same as what you have here: 1011 0000. Okay, so that's why I said just now that by default all computing systems use the 2's complement. All right, so when you key in a negative number in your system, all right, it will automatically show you as the 2's complement, okay, which is what you can see here. All right, so that gives us an idea of how the 2's complement works. Okay, so again, this is just to give you an idea of comparison between the 3 different techniques. Okay, again, I think the most important is as long as you know how to represent a number both in positive or negative, then it is fine. All right, depending on whether it's sine magnitude, 1's complement or 2's complement. Okay, so coming back to this question, okay, why, how does this thing work? All right, so if you have this code running, all right, and you have this loop running at 10 times with this initial value, what will happen? Okay, so this again comes down to the specific system you're going to run this on. Okay, so that's why when, for example, if you use Sunfire, all right, in Sunfire, the compiler uses 4 bytes, all right, to represent your integer data type. So if it uses 4 bytes and since 2's complement is the default value, the largest positive number, okay, is given by this. All right. So if you come back here to this slide, you can see that the okay, I think this is easier to see. Now, if I look at this, just 4-bit value over here. All right. If I take, for example, this 2's complement, okay, what you observe? You observe that the highest or the biggest value is +7, and the smallest value is -8. Okay, which is this and this. Okay, so how do you get this and this? Basically, the highest or the biggest positive value is, if it's a 4-bit system, the most significant bit is 0, and I have remaining ones. Okay, if it's an 8-bit system, okay, if I say I use the 8-bit system, the same thinking applies. The biggest or the highest positive value will be, again, most significant bit 0, followed by 7 ones. Okay, the smallest negative value, is when the most significant bit is 1 and the rest are 0. So same thing over here. Okay, so of course, instead of just trying to figure it out through ones and zeros, all right, there is a easier way to do it. Okay, to know what is the most biggest or smallest number, that is using this negative to the power n minus 1 to negative to the power n minus 1 minus 1. Okay, so let's see how to apply this. So if I say if it's a 4-bit system, okay, 4-bit system, then n is equals to 4. So if n is equals to 4, the smallest number is 2 to the power of, sorry, minus 2 to the power of 4 minus 1, which is minus 2 to the power of 3, which is minus 8. And the biggest number will be 2 to the power of 4 minus 1 minus 1, which is 2 to the power of 3 minus 1, 8 minus 1, which is positive 7. All right, so this formula here is the one that is able to give us the range, okay, given any number of bits in the system. All right, you just need to substitute n with the actual number of bits okay, that you're using to represent the number. All right, so this gives us an idea of the smallest number and the biggest number that you can represent, depending on how many bits you are using to represent that particular data type. All right, so that is how you are able to relate back to this question over here. All right, so since I use 32 bits for integer in the Sunfire, the largest positive integer is this, 2 to the power of n minus 1 minus 1. Okay, so 2 to the power of 32 minus 1, which is 31, minus 1 will give me this. Okay, all our classes are scheduled for 3 hours, 6:30 to 9:30. Okay, so we will usually go for about 1 hour or so, then we will have a break, and then we will carry on, and then we will see. Usually, most of my classes will end around 9, right, unless we really have to finish up something. Okay, so again, I understand that most of you all are, I mean, all of you are working adults, and you all have family to go back to, children to take care. Okay, so if you can't really stay, of course, those of you who have to have the attendance because of funding or some sponsorship or things like that, then please ensure your attendance is taken. All right, that means you are there for the full class. Okay, but if not, if you need to urgently go off somewhere or something, then it's fine, but just try to catch up, okay, by seeing the recordings later on. Okay, so this largest positive integer is this. All right, so what happens once I hit the largest positive integer? Okay, so let me go back to the table here. Okay, so when I hit the largest positive integer, okay, what happens? So what normally happens? So if you look at the way in which we count, okay, so if I say 0, 1, 1, 0, 0, 1, 1, 1, so this is actually 6, this is actually 7, okay. So in terms of binary, what happens? When I hit 0, 1, 1, 1 and I count one more, I will automatically go to 1, 0, 0, 0. Right, and 1, 0, 0, 1, and so on. So when I hit the highest positive value and I increment by 1, what will happen is I will immediately roll back to the smallest negative value, which is -8 and -7 and so on. Okay, so from +7, if I increment by 1, I will actually roll over and start from -8 and count towards 0. Okay, so that's basically what happens when you hit the limit and you still increment. You sort of roll over. Okay, so that is the explanation for this. So when I start off with this number, okay, so the last 2 digits is 40, but I know that I can only go up to 47. So when I hit 47, what happens? When I increment by 1, I will actually roll over. Okay, so this highest number, like I said, is the point where the most significant bit is 0 and everything else is 1. Okay, but the moment I increment by 1, it will actually roll over to become the smallest negative number. Okay, so it will become this. Okay, the smallest negative number. Okay, and then you will count upwards towards 0 after that. Okay, so again, this question is sort of related to how we represent negative numbers, all right, and also the idea of understanding how many bits are used to represent those numbers. Okay. Now, how about fractional part? So we talked about the fractional part earlier on. Now, the fractional part is done the exact same way. So in 1's complement or 2's complement, you do the exact same thing. That means if it's 1's complement, you just do the flip. Okay, you just do the flip. For 2's complement, you do flip and then you do +1. Okay, so for example, if I take this value here, 0101.01, and I say I want to do the 2's complement, I do the same thing. I flip 1010.10, Okay, and then I add 1. So I'll get this. Okay, so it's the same technique, okay, that you just apply across the entire number that you have. Okay, so let's look at how to do some addition and subtraction for 2's complement numbers. Okay, so firstly, what we're going to do is we're going to perform the binary addition. All right, and we're going to ignore the carry of the most significant bit. So if there's a carry out, we just ignore it. All right, and then we check for overflow. So what is overflow condition? Okay, so we can easily say that overflow condition is basically the case where the answer is not going to make sense. Okay, so when do we say the answer doesn't make sense? That means, for example, if I take 2 positive numbers and I add them together, but the answer is negative. Okay, or if I take 2 negative numbers and add them together and the answer is positive. So both these cases, you can say that the answer doesn't make sense. All right, so you can say it's an overflow condition. All right, another way to detect overflow is this check where the carry in and carry out of the most significant bit are different. All right, so let me show you. All right, so the addition, okay, or subtraction is basically done by addition. All right, so if I want to do a subtraction, okay, a minus b, it is the equivalent to saying is a plus minus b. So mathematically, we know this is correct. All right, and what we need to do is, if I want to do a subtraction of a and b, or b from a, then I do the 2's complement of b, because when I do the 2's complement of b, I get negative b. All right, and then after I get that, if I do the addition, that is equivalent to doing this a add with negative b, okay, or the 2's complement of b. All right, so why we do it this way, all right, is because we want to reuse the hardware that we have. Okay, so this one we will sort of better appreciate when we look at the MIPS processor later on. But basically, what we want is to do this addition requires a certain amount of hardware to be available on your processor. Okay, so what we want to do is, since we already are going to build this hardware to do the addition, we can just stick to the same hardware to do the subtraction, but all we need to do is do a complement for the second operand. Okay, so this sort of allows us to reuse what we have instead of trying to create 2 separate blocks. Okay, one for addition, one for subtraction. All right, which will be a waste. All right, so this allows us to sort of reuse existing blocks to solve what we want. Okay, so let's look at this example here to understand how we can look at overflow condition. Now, if I take this example 0 1 0 1, okay, and 0 1 1 0, okay, if I want to do the addition, what will I get? 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0 carry 1, and 1 plus 0 plus 0 is 1. Okay, so now how do I interpret this value? Okay, so this is the thing we must understand when we deal with negative numbers. All right, how do I interpret it correctly? Now, when I look at this first number over here, okay, and this second number over here, you see that for both of these numbers, the most significant bit is 0. Okay, when the most significant bit is 0, there is nothing to worry about, because you can decode it or interpret it in the same way as you do any binary number. Okay, so for example, if I were to just use my calculator, okay, so of course, once you get used to it, you know this is 5 and this is 6. All right, but let's just use a calculator here. So if I would be keen over here and say 101 is 5, all right, and 110 is 6. So I know that the first value is 5, the other value is 6. Correct. Now, the result that I get 1011, what is the answer here? The answer here is 11. Okay, the answer here is 11. But how can it be 11? It doesn't make sense. Okay, why it doesn't make sense? Because we are saying that we are using a 4-bit 2's complement system. Okay, so a 4-bit 2's complement system means the range of numbers that I can represent is only from here to here, because now I'm looking at both positive and negative. And 11 is beyond this range. Okay, 11 is beyond this range. So even though this is 5, okay, this is positive 5, this is positive 6, the answer that I get is actually 1011. Okay, so how do I interpret this answer? If you say that this answer is 11, then you are interpreting it wrongly, because in order for this answer to be valid and 11, then you cannot say you're using a 4-bit 2's complement system. Okay, so you must always relate the answer that you get to what is the representation you're talking about. In this case, the representation is, it is a 4-bit 2's complement system. Okay, so if it's a 4-bit 2's complement system, then the answer 1011 cannot be 11. All right, and this is what we call an overflow condition. All right, and like I said, how do you know it's overflow? Because of the two checks. The first check is the addition of two numbers of the same sign give you the answer of a different sign. Okay, the first value is positive, second value is positive, okay, but yet my answer is negative, because the most significant bit is 1. Okay, so since the most significant bit is 1, so it doesn't make sense, correct? Two positive numbers add together, but my answer is negative, so it doesn't make sense. Okay, the other check is what the carry in and carry out of the most significant bit are different. Okay, so how do I look at this check? You can see that over here, okay, over here the carry in. So just now over here when I did, so this is the most significant bit. Okay, so what was the carry in? 0, 1 plus 1, 0, carry 1, correct? So this was the carry in. But what is the carry out? 1 plus 0 is 1. So is there any carry out? No, there is no carry out. So carry out is 0. So the carry in to the most significant bit is 1, but the carry out, okay, there is no carry out. So the carry out is 0. So if the carry in and the carry out are are different, then it is also a sign that the overflow has occurred. Okay, so the overflow only occurs when you are able to identify one of these two conditions. All right, now let's look at the next one. 1001 and 1101. Okay, so now this is another interesting thing. How do I interpret this 1001? Because if I key this 1001 into my calculator, I will get this as a value of 9. Okay, if I key in 1001 into my calculator, it is equivalent to positive 9. But is this interpretation correct? Okay, it is not correct in this context. Why? Because again, we are dealing with a 4-bit 2's complement system, which means that the moment I say 2's complement, the most significant bit is 1, means it is a negative number. Okay, if the most significant bit is 1, means it is a negative number. So this representation 1001 cannot be plus 9. Okay, it cannot be plus 9. So how do I figure this out? How do I know the actual representation? So this is not correct. Okay, so this is not correct. 1001 is not equals to positive 9. So what is it equals to? Okay, so this is where you must understand that whenever you deal with negative numbers, that means the most significant bit is already 1, you cannot take the interpretation of the calculator as a value. All right, what you need to do is you need to find the actual numerical value and then put a negative sign in front of it. Okay, so what do I mean by finding the actual numerical value? So what you need to do is you need to do the 2's complement of whatever binary value you have. Okay, so let me show you what we need to do. So the current value I have is 1001. Okay, but we know that that is a negative number because the most significant bit is 1. Okay, the moment you know the most significant bit is 1, you cannot take a direct interpretation. What you need to do is you need to do the 2's complement. So the 2's complement means I flip and I add 1. So what will I get? 0, 1, 1, 1. Okay, now 0, 1, 1, 1. Now I can put in my calculator and I get a value of 7. All right, but since I know that this is actually a negative number because the most significant bit is 1, what I then need to do is put a negative in front of it. Okay, so that is how you interpret any binary number if it is 2's complement and the most significant bit is 1. Okay, if the most significant bit is 0, like this example here, then there's no problem. Okay, you can straight away put in a calculator and you can just take the value as it is. But the moment that the most significant bit is 1, then the number that is representing is actually a negative number. So to know the actual value of this negative number, what you need to do is you need to do the 2's complement. Okay, you need to do the 2's complement and then you need to add 1. All right, so 1001 is now going to be represented as negative 7. So this is actually negative 7. Okay, can you all try for 1101 and see that is negative 3? Okay, I'll just give you 1 minute to just try for yourself. See that you can convert 1101 and you actually get it as a negative 3. Okay, so just try it now and I will show you in a bit. Okay, so again, this is only is what you need to do only if the most significant bit is 1. That means it is a negative number. Yeah, so basically you do the 2's complement, correct? So you flip it. So 1101, you do the flip, so it becomes 0, 0, 1, 0, and then you add 1. It becomes 0, 0, 1, 1. So 0, 0, 1, 1 actually is 3. But since the original value has the most significant bit as 1, that means I put a negative 3. So this is negative 3. Okay, so once you know how to interpret it, okay, you can again see that negative 7 plus negative 3 is supposed to give me negative 10. Okay, but again, this is beyond the range. Again, beyond the range. So 1 plus 1, you get 0, carry 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 0, carry 1. So the most significant carry you can ignore. So this one you can ignore. Okay, you can ignore. No need to worry about this. But we only focus on the most significant bit right now. So you can see that most significant bit is 1 negative number, most significant bit is 1 negative number, but the answer is 0 positive number. All right, so there is something wrong. 2 negative number add together, but the answer has the most significant bit as 0. Okay, or the other check is the carry in and carry out. So we can see that for this, the carry in is 0. But over here, the carry out is 1. Okay, so that is another check. I can also confirm that this is a overflow condition. All right, so again, this overflow is important because we need to know whether this overflow has occurred. All right, because if it has occurred but you do not realize it has occurred, then you will interpret the number wrongly, correct the answer wrongly, and then you can mess up. Okay, what you're trying to do. Okay, so these are just some examples. All right. So which of them are overflow? Okay, so to put it simply, you can see that the overflow condition occurs. Okay, whenever this you have two negative numbers. Okay, and the answer is positive. Okay, in this case, two positive numbers, but the answer is negative. All right. So you can easily just check by looking at the most significant bit and the answer to see whether there is overflow condition. Okay, to do subtraction, okay, like what we said just now, what you need to do is you take the actual number and perform a 2's complement. So if I want to do 4 minus 7 is equivalent to saying 4 plus negative 7. How do you get negative 7? You take actual 7, which is 0, 1, 1, 1, and you do the 2's complement. So you get 1, 0, 0, 0, then you add 1. So you get 1, 0, 0, 1. So that is your negative 7. Okay, and again, once you do that, you can then check for overflow, okay, based on the result. So in this case, you can see that for this last example, you have two negative numbers add together, but you have a positive answer. So it's an overflow condition. Okay, so the ones complement addition is similar. Okay, so the question is why the 4 doesn't need to convert. Yeah, you only need to do 2's complement for the negative numbers only. Okay, so in this case, we are each of this we are replacing the negative with a plus with the negative of the second operand. Okay, so the first operand is still in the positive, so we don't need to do 2's complement. Only when we convert it to a negative, we do the 2's complement. Okay, so the ones complement is another technique, but it's not so important. Alright, so we will skip this part. As long as you understand the 2's complement, that is enough. Because the ones complement is not really used in systems, so I think we can skip this part here. Okay, so this excess representation, again, I'll not go through, it's just for information only. It's just to show you that there is another way of representing numbers. All right, so in this case, this excess representation, basically what it does is it just shifts your entire range to a new starting point. Okay, so for example, if I say that I have 3-bit numbers, okay, the 3-bit numbers, this is the full representation. Okay, but if I say I want it to be excess 4, that means the value 4 is equivalent to the new 0. We call it the new 0. Okay, so this 4 is now the new 0, and then from there you count forward and you count backward. Okay, so that is basically what is called the excess representation. All right, again, this is just for information. We will not discuss too much about it. Okay, but it's just to tell you that this is another way in which numbers can be represented. All right, so now let's come to another part. This is the last part of this chapter, all right, which is representing real numbers. All right, so what do you mean by real numbers? Real numbers are numbers that can be very, very small and can be very, very large. All right, so in real life, okay, you will deal with very small numbers, 0.00562, or very big numbers, correct? 200,000, 555 or something like that. Okay, so we can have very small numbers, very big numbers, and those numbers can also have fractional component, correct? So you can have 250,000 with decimal values of 5, 6, 7, 8 or something like that. All right, so how do I represent these real world numbers in using binary bits? Okay, so one technique is, of course, you can use what you call a fixed point representation. When you say fixed point representation, is basically you split up the number of bits you have such that one part of it is the integer part, the other part is the fractional part. Okay, so in this simple example, if I say I have 8 bits, I say 6 bits is the whole number part and 2 bits is the fractional number part. Okay, so this is one way of doing it. All right, so if you do it this way, of course, it still works. All right, but of course you are very limited in its expansion. Correct. That means if once I fix only 2 decimal values or 2 decimal places, then there is the maximum or the smallest resolution you can have. Okay, nothing smaller than that. All right. So again, if you use 2's complement, you do the same thing. The most significant bit can represent positive or negative numbers. Okay, so this is of course an easy way. All right, but it is very limiting. Okay, to the range that you can represent. Okay, because you want to be able to have very small and very large numbers, okay, to be represented in our system. So that is where this this technique or format called the IEEE 754 floating point representation comes in. So this is a very nice way, okay, in which you can represent very small and very large numbers using a string of binary bits. All right, and how it works is you are going to represent the number in 3 parts: the sign, the exponent, and the mantissa. Okay, so we're going to be focusing on this, the single precision, which is 32 bits, and we're going to understand how it works. Okay, so what I'm going to do is I'm going to go through the next slide, all right, to see it actually being applied. Once you understand this slide, then it's easy to do it again on your own. Okay, so what you want to do is you want to represent this value negative 6.5 in this IEEE 754 format. Okay, so how do I go about doing this? So the first thing is the sign. Okay, the moment the value is negative, the sign bit is going to be a 1. Okay, so that is the first thing. Okay, if the number is positive, the sign bit is 0. The number is negative, the sign bit is 1. Okay, so that is the first thing. Okay, so there's a question, where will the lecture recording be uploaded? Okay, so similar to what we did for last week. All right, so every time the lecture is over, I will send out 2 things. One is the actual Zoom recording link. The other one is I will upload to YouTube as well. All right, I'll send you all the link. All right, so if you look at the last announcement, last week's announcement, I sent both the links. So every week I will do that. Okay, so coming back to this, so the first thing is the sign bit. Okay, so in negative it is 1, positive is 0. Now the second step is, okay, so put it here. First the sign bit. The second one is you normalize. So what is normalize? Normalize means I want to represent it such that it is just a single digit and the decimal point and then everything else. Okay, now 6.5, how do you represent it in binary? So the first thing is convert 6.5 to binary. So 6 is 110 and 0.5 is 1 here. Okay, so if you don't remember, whenever you have decimal point, okay, to the left it is 2 to the power of 0 times the value 2 to the power of 1, 2 to the power of 2, and so on. To the right is 2 to the power of -1, -2, and so on. So 0.5 is half. So it is 2 to the power of -1. So that is why this bit is 1. Okay, so 6.5, okay, in decimal value, convert to binary is 110.1. When we say we want to normalize it, we want to represent it in this form, where you shift the decimal point such that there's only one digit in front of the decimal point. So I need to shift this 0 until there's only one digit in front of it. Okay, so how much did I shift by? I shifted to the left by 2. So I shifted to the left by 2. That is equivalent to multiplying by 2 to the power of 2. Okay, it is the same like your maths. All right, so if you imagine that is 6.5, I shift in decimal, I do a shift is equivalent to what? 0.65 times 10 to the power of 1. All right, so in maths we do the same shifting and you can multiply by 10 to the power of something. Correct? And why is it 10? Because it is base 10. Correct? When we deal with normal numbers. So the same concept applies here. So since I shift to the left by 2, I multiply by 2 to the power of 2. So this 2 is because it is a base 2 system. Okay, this 2 is because I shifted by shift by 2 bits. All right. So once you have this is what we call the normalized representation. Okay, once you have the normalized representation, it's very easy. The next step is you figure out the exponent and mantissa. So what is the exponent and mantissa? Okay, to find the exponent, all you need to do is you take 127 plus whatever is the value over here. Okay, whatever is the bits you shifted by over here. So if the power here is 2, then I say 127 plus 2. All right, so what I'll have is 129, and 129 you just key in your calculator, you'll get this binary value. So that is what comes here as the exponent. Okay, so let me repeat that. So to find the exponent, all you need to do is take 127, add with whatever number is the power of the base 2. And whatever number you get, you represent it as an 8-bit binary and put it here as the exponent. Then what is the mantissa? Mantissa is whatever is left after the decimal point. Okay, so mantissa is whatever is left after the decimal point. So 101 is left. So 101 actually comes here, and everything else will be filled up with zeros. Okay, so this 101 is this 101 here, and the rest of it is all filled up with zeros. So total is a 32-bit representation. So the rest of the bits will all be zeros. Okay, so there's a question, how do we know it to shift by 2 bits? Okay, so you shift, like I said, to normalize it, this is the representation we want. We want it to be such that you have a single digit and then decimal point and everything else. So we just need to shift until you reach the 1 digit to the left. That's it. Then you stop. Okay, so these are the only 3 steps that you need to do. First step is, okay, you negative number, the sign bit is a 1. All right. Next, after that, you convert your value to a binary form. And once you convert to a binary form, you normalize. So to normalize, you shift the decimal point until you have only a single digit at the left-hand side. Then depending on how many bits you shift, okay, that will be the power that you raise it to the 2. And that value, you add 127, you get the exponent. And whatever is left, which is the right of the decimal point, will be the mantissa. Okay, so that mantissa, you just extend zeros until you fulfill the 32 bits for the whole representation. So this is of course the final answer. All right, but looking at ones and zeros in such a long string is of course confusing. All right, so in most cases we convert it to hexadecimal. Okay, how do you convert to hexadecimal? We just group them into 4s. So 1100 is 4000, 01101, and the rest are all zeros. Okay, so this 1100 is C, this is 0, 1101 is D, and the rest are all zeros. Okay, so that is how you get the final answer here. Okay, so this IEEE 75 floating point representation is a common way in which our calculators and everything work. Okay, so you have the 32-bit version and 64-bit version. Okay, so it's just an extension, but it's the same concept. All right, so again, I think the key thing is if you look at this entire 32-bit value, how do I interpret it? It all depends on how you looking at the representation. If I say that this 32-bit value is an integer and is represented in a 2's complement form, then we say that this is a negative, this large number over here. Okay, but this same 32-bit value, I say that this is actually a floating point representation in the IEEE 754 format. Then you actually say that this is negative 6.5. Okay, so it all comes down to the understanding of what these ones and zeros mean to us. Okay, so it can represent a character, it can represent an integer, it can represent a float. Okay, all depends on what is our understanding of the data. Okay, so that is how I think that's the main idea of this chapter, to make us understand that ones and zeros are just there. Okay, but it's up to us to decide how we are going to interpret it. Okay, and use it in our system. Okay, so yeah, I have a nice animated video, all right, in my YouTube channel, so you can sort of look at that to again recap how to go about doing this conversion. Okay, so that brings us to the end of this chapter over here. Okay, so now it's 7:36. I think it's about time to go for a break. Okay, so we'll take a 15 minutes break. So 7:50. Okay, 7:50 we will come back here, and then we will start on the next chapter on MIPS. Okay, so we'll take a 15 minutes break. Okay, and we'll come back at 7:50. Okay, to start on the MIPS chapter. Okay, in the meantime, if you have any questions, you can just put it in the chat. Okay, later when everybody is back, I will address those questions. Okay, so thank you. I'll see you all back here in 15 minutes. Okay, so welcome back. So there's a question here. What happens when there's overflow and what can be done to remedy this? Okay, so basically, we can detect overflow. All right. I mean, the whole idea of overflow is to have a better understanding of our own limitations when we write software. So going back to that example, that exam question example, okay, so you can sort of see that if you write your code without understanding what is happening, then you will not be able to sort of interpret the data in a correct way. Okay, so let me just share that again. Okay, so if you look at this example, all right, if you a person who writes the code without understanding that this overflow is going to happen, all right, and you just run it, all right, you will find that the answer is going to be wrong, all right, or it's not what you expect. All right, so that is why the concept of understanding. Okay, so instead of saying that you want to detect overflow or things like that, more of understanding when the overflow will occur. All right, and you should be able to know when the overflow will occur by understanding how data is going to be represented in the system. Okay, so in this example, okay, so since this Sunfire platform uses 4 bytes to represent integers, all right, we know that this is the largest value. All right, so if I try to represent a number bigger than this value, it's not going to work. I mean, bigger than this largest positive integer. Okay, so what is the solution to this? Let's assume that I really need to count up to a value that is bigger than this number over here. So what is the easy solution to this? Can anybody suggest to me? Okay, so there are two easy ways to do it. Okay, so one is, of course, you declare the variable as unsigned variable. So when you declare a variable normally, okay, the default setting for the compiler is to take it as is a signed variable. Signed variable means, okay, it is both positive and negative. Okay, so the easier way is to just say is unsigned. Okay, so when you say is unsigned, you are telling the compiler that this variable is only going to be pure positive numbers. So in that case, you're not going to have any negative representation, but you can have the full range to represent positive numbers. So that is one easy way to sort of resolve this. Okay, so how to decide whether you need to convert? All right, so usually whether it's one's complement or two's complement, it would be mentioned in the question. All right, and in most cases, like I said, we will always use two's complement because that is the default approach. And you only need to look at the two's complement when there is a negative number involved. Okay, so if you look at all this example, when the most significant bit is 0, it is interpreted as positive. All right, so there is nothing you need to worry about. But the moment the most significant bit is a 1, that is treated as a negative. So that is where the two's complement comes in. Okay, if I give you a negative number, then you need to do the two's complement to know the representation in binary. Okay, so that is where the two's complement and the negative representation comes in. Okay, so hope that clears up any doubts that you have. Okay, let's move on to the next chapter on the MIPS. Okay, so this chapter on MIPS is basically a very big chunk. I think there are a total of 3 set of slides, okay, that talk about MIPS. Okay, again, this is just, I would say, about half of the, let's say about half, about maybe about 60% or so of what we cover for MIPS in the CS2100 course, okay, where we go into more advanced architectures. All right, but here we scale it down a bit, so you only focus on understanding assembly language, all right, and how the processor actually interprets assembly language instructions. Okay, so in this MIPS section, which is basically going to take up the rest of the weeks for the first half, okay, of this semester, we're going to cover a few things. So firstly, we're going to understand the processor architecture. We're going to understand how a high-level program in C is broken down to assembly language code, okay, and then we're going to look at how assembly language code is decoded and executed by the processor. Okay, so we're going to go into a very low level of hardware understanding to look at how the processor actually works. Okay, so it's going to be very interesting. Okay, but at the same time, again, not everybody likes this because they feel that, you know, it's like too much of hardware stuff which they don't really need to know because, you know, they're doing high level software and things like that. Okay, again, this is the reason why this is still an important concept is because we want, as computing students, we want you to appreciate and understand what is really happening at the back end. Okay, because when you understand what's happening at the back end, okay, or the lower level, okay, you sort of appreciate why certain things run better on maybe one platform compared to another platform. Okay, so it's about how software can be optimized to make better use of the hardware. Okay, maybe a simple example I can give is, if you remember, about 2 years ago when Apple launched their M1 processors. Alright, so all the while they're using Intel, alright, and then they switched over to integrating with ARM and they launched the M1 processors. Okay, so if you remember when M1 first batch of MacBooks came out with the M1 processor, there were a lot of very good performance benchmarks that they mentioned, but all of those that they mentioned were only on their own software, like Final Cut Pro, Pages, Numbers, their browser and things like that. Okay, why? Because their software is optimized to run on their hardware. Okay, so other software like Microsoft Office and other development tools and so on, they did not have a compatible version for the M1 processor yet. All right, so they had to tweak their software the way it was compiled or it was written to match the new hardware, which was the M1 processor. Okay, but once they did that, then they too saw a good performance increase. Okay, so that is why when you write the software, when you understand how the hardware is configured or wired up, okay, and you can optimize your software to take advantage of this hardware, you will be able to achieve a lot more better performance, okay, in your system. Okay, it's just like your laptop with GPU and no GPU. All right, so if you play games, all right, without a GPU and with GPU, it makes a big difference. Correct. And how does it make a big difference? Because the game software knows that you have a GPU, it will optimize the GPU to make your gaming experience better. Okay, if you don't have a GPU, then it just relies on your processor to do everything. Okay, so that is another example where you can say that when the software is better able to appreciate and maximize the use of the hardware, you are able to get better results. Okay, so basically in this we are going to looking at all this stuff, all right, instruction set architecture, assembly language, and so on, all right, and some basic operations using the MIPS instruction set. Okay, so just to recap, this is what we saw earlier. Okay, that a very high level program in C, okay, like this. When you click on compile, okay, what it does is it translates it into what we call assembly language. Now, what is assembly language? Assembly language is basically an intermediary between the high level and the lowest level, which is machine language. Okay, what is machine language? Is basically the only language that the computer understands, which are ones and zeros. All right, but if I give you a bunch of ones and zeros and I ask you to interpret it, we will go crazy. Okay, looking at all the ones and zeros. Okay, so that is where this assembly language actually plays a big role, because at assembly language level, we are able to quickly and very easily relate to both ends. Okay, so from assembly language, I can easily translate it back to C, and from assembly language, I can also look at the machine code. Okay, so it's a very nice intermediary step, okay, that links up the higher level to the lower level. Okay, and this assembly language is very specific to the processor that it is being compiled for. Okay, so if I take this same high level language, okay, and if I compile the code and it runs on the ARM processor, I will get a specific set of instructions. If I run it on the Intel processor, I will get another set of instructions. Okay, if I run it on the MIPS processor, I'll get another set of instructions, because these assembly language instructions are very specific to the hardware we are dealing with. Okay, so that is why programming in higher languages is of course still the most preferred choice, because you always have the flexibility to switch to any hardware as long as the compiler supports it. Okay, so that is the advantage. So your compiler must be able to automatically switch between supporting different processors. So the same high level code that you develop can run on multiple platforms at the same time. Okay, so in order for us to understand and appreciate this, that is where the instruction set architecture comes in. So that is basically the understanding and the link between the hardware and the software. All right, so again, these are just some of the different examples. Okay, we're going to go into that. Okay, and like I said, the machine code is the ones and zeros, but to easily interpret the ones and zeros, the assembly language is there. Okay, so as a question, different OS is created because of the compiler. Okay, so OS is different, compiler is different. Okay, OS is basically the operating system. That means it is the higher level system that manages your overall platform. When we say compiler, that is specific to the development tool that you are using. Okay, so for example, if you are running, okay, a particular compiler. So if, let's say you install a compiler on your system. Okay, let's say you install Visual Studio, all right, and then you write some C code or C++ code or whatever. Okay, so that Visual Studio will compile the code that you have written to execute on the processor that is running on. Correct. So in the same Visual Studio code, a Visual Studio development tool, you can install on an Intel PC, you can install it on a AMD PC, and both will run and both will give you the same result. Correct. But the difference is what? The difference is, even though the high level code will be the same, the lower level code is actually different because you have two different processors. Okay, so that is dependent on the compiler. So the Visual Studio that you have must be able to support the processor that it is running or you want to run the code on. Okay, so if I install Visual Studio on a AMD processor and I want to run my compile code on it, then it must support generating instructions that is compatible with the AMD processor. Okay, if I run it on an Intel platform, then it must support the Intel system. Okay, so that is where the compiler comes in. Okay, in most cases, like I said, compilers now are very smart to automatically switch, okay, depending on what is the project you created, what is the hardware you're running on, and so on. So generally, a lot of this sort of settings are quite transparent, okay, because once you create a project and you say that this is the target platform or this is the thing you want to run on, it automatically will be able to generate the correct or choose the correct processor compiler for you. Okay, so but you always have flexibility to change it, okay, in some settings or whatever. All right, so now let's look at this example code over here to understand the interpretation of a higher level code to assembly language code. So over here, what you have is you have a very simple loop, okay, which we know, okay, in C. Now this loop is having two variables, I and result, okay, and I'm running a loop for 10 times. Okay, now if I were to interpret this into a sequence of, let's say, pseudo instructions, it will look something like this. Okay, where I do the addition, I increment I, and then as long as I is less than 10, I repeat. Okay, so this is the sort of okay, so it's more of a pseudo code than assembly code, okay, just to interpret the loop into a sequence of steps. Now, let's look at these steps and how a computer or a computing system is going to perform these steps for us. All right, so the underlying hardware, all right, though it's very complex, okay, we can break it down into a few major components. So the first one is the processor. Okay, so again, this processor is about the actual core, the processor core. So you can think of it as, if you say it's a handphone, it's most likely an ARM processor. If it's a desktop or laptop, it's like an Intel or AMD, all right, or maybe even the new ARM-based M1 and so on. All right, so the processor is basically the core which is going to perform all these computations for us. All right, the other thing is, of course, you need memory. Okay, any computing system needs memory because you need to store your program, you need to store your data, your variables, everything. Okay, now how do I interconnect the processor with the memory? So that is where the bus comes in. Okay, so a bus is just a general name for a group of wires. All right, so you have a lot of wires that are connecting the processor to the memory. All right, and of course you can break it down into 3 separate buses. Okay, so we call it the address bus, data bus, and control bus. Okay, but for our first level understanding, we will take it as just a single bus. All right, to bridge between the processor and the memory. Now, let's look at what happens. So at the very first instance, all right, this is basically what we want to do. We have these 3 instructions, okay, which are in the memory, which is part of the code. Plus, we also have these 2 variables, correct, which we have declared. Okay, so the result and I are 2 variables which are also in memory. The code that is supposed to perform this loop is also in the memory. Okay, so what do I need to do? Okay, in order for the processor to execute these instructions, it always goes through this 3-step process, or we call it 3 main cycles. What are the 3 main cycles? F, D, and E. Can anybody tell me what are these 3? What these 3 represent? F, D, and E. You may have heard this before. No? Okay, so you have not heard it before. Basically, FDE is called fetch, decode, and execute. All right, so this is basically the 3-step process that your system is going through for every single instruction that you have in your code. Okay, so I need to fetch the instruction, I need to decode the instruction, and execute the instruction. Okay, so that is basically what is sort of shown here. Okay, I need to fetch the instruction, which is what I want to do. Then I need to decode the instruction. I need to make sense of this instruction. And finally, I execute. Okay, so after I execute it, then I will get some results and so on. Okay, so let's look at this step by step. Okay, so the first thing is, we know that in order for me to do the fetch instruction and execute, I need to be able to store my instructions, okay, inside a space in the processor. All right, so that is okay. So inside the processor, you have a lot of sort of storage spaces, which we call as registers. So these registers, you can think of it as a small amount of memory that is internal to the processor. That only the processor is able to access these memory regions. Okay, so to store the instructions, I need some space. Now another thing is, whenever we write code, we make use of a lot of variables, correct? And these variables are stored in the memory. Okay, but memory access is always slow. Okay, it's always very slow. Okay, if you look at the history of technology, the processor has been able to almost double up, okay, in the speed, okay, every few months. Yeah, I mean, at least a few years ago. All right, but the problem has always been the memory has always been very slow in catching up. So your processor can do things very fast, but the memory access is so slow. So eventually the whole system becomes slow. All right. So there's always a lot of research going on into what can be done to make or to have some improvements. All right. So these are things that I will talk about later as well. Okay, things about cache, virtual memory, and so on. Okay, but for now, one of the easy ways, okay, in which we can reduce memory access is if we can keep some amount of these variables in the local register space. Okay, so these are all the registers that we have. Okay, now instead of keep on trying to fetch I and result from the memory, what I can do is I can use the internal space that I have, the register space that I have, and take a copy of that data and put it into my internal registers. So that is what I'm doing here. Move data into the registers. Okay, so by doing this, I'm able to avoid the need to constantly keep reading from memory. So again, why we want to do this is memory access is very slow, all right? And if I keep on reading from the memory, I will waste a lot of time. All right, and since I know that these two variables are in memory and I need to use these two variables quite regularly, why don't I load them into memory first? So these two instructions here, what am I doing? I say load I into R0 and load result into R1. So R0, R1, and so on, these are all the registers that I have. Okay, so in these first two lines here, I am loading the value that is in these variables into my internal registers R0 and R1. Okay, so I execute the first instruction that says load I into R0. Okay, so whatever value is in I comes into R0. And in the second instruction, I say load result into R1. Okay, so by doing these two steps, what I am now able to do is for the rest of the instruction that need to use I and result, I actually don't need to fetch from memory. I can use the data already stored in R0 and R1. Okay, so that will save me a lot of time. Okay, it will save me a lot of time because I don't need to have so much of memory access after that. Okay, so if you notice between these two slides, over here, it is still the use of result and I. But once I have loaded I and result into R0, R1, subsequently, I only need to use R0 and R1 in that loop. All right, so with this change, all right, I am now able to very efficiently use the internal registers instead of relying on the memory access so much. Now let's look at the loop itself. So the first instruction says take R0 plus R1, do the addition and put into R1. Okay, so since R0 and R1 is already there, now I need to decode this instruction to say that I'm supposed to do an addition. So this addition, okay, and subtraction and all of the stuff is done inside the ALU. Does anybody know what ALU stands for? Okay, so ALU stands for arithmetic and logical unit. Okay, arithmetic and logical unit. So this ALU is a part of every processor. Okay, so that is basically the one that does a lot of the computational requirements. Okay, your addition, subtraction, multiplication, division, okay, and so on. In some processors, maybe you have a few different hardware blocks to do different types of computation. But at least the most basic one, addition, subtraction, okay, and maybe multiplication and so on would be done in the ALU. Okay, so this ALU is the one that is supposed to perform this addition. So once it does the addition, it generates a result and it puts the result back into R1. Okay, because that is what the instruction is telling the processor to do. Take R1, take R0, do the addition and put the result back into R1. Okay, so that is what the instruction is telling it to do. Okay, and then what I need to do? I need to do the next instruction, which is R0 increment by 1. So I take R0, add with 1, and take the result, put back into R0. So I take R0 value, increment by 1, and take the result and put back into R0. So R0 will now increment by 1. Okay, so that is the second instruction I'm executing. Okay, so you can see that, okay, what this few slides is showing us is the step-by-step process. What is really happening when you take that loop and you try to execute it at the hardware level. All right, so it comes down to a lot of steps. All right, the first step is taking the variables, putting them into registers, then subsequently translating each assembly language instruction line by line. Okay, so right now we are not looking at the actual instructions yet. We are still looking at it more from the pseudocode perspective. Okay, but this is basically very similar to what assembly language instructions are going to be doing. Okay, they're going to break down a very high level code into very simple step-by-step instructions. Okay, which is what we are seeing here. We take R1 at 0, put into R1. Now we take R0 at 1, put back into R0. Okay, and then the last instruction, which is if R0 less than 10, then we repeat. If not, we exit the loop. So this is basically the sort of checking, correct, conditional code checking to decide whether we go to a particular line or we skip to another line and so on. All right, so in a sense, it is similar to the loops, the if else that you see in your normal C code. Okay, so we're going to execute this. If I less than R0 less than 10, you repeat. Okay, if not, you exit the loop. So again, we repeat. Okay, so again, this thing will keep on happening, all right, until you reach a point where the last iteration of the loop is there. So R0 is 10. So once R0 is 10, the condition will no longer be true, correct? Because this condition says that only if R0 less than 10 and repeat. But once R0 already hits 10, okay, once R0 hits 10, you will no longer repeat. All right, so what will happen? Okay, so once you no longer have to repeat, that means you're going to exit the loop. So when you exit the loop, okay, what you need to do? Okay, so what you need to do is you need to make sure you update the variables from the memory with the correct answers that are from the registers. Okay, because you remember that ultimately in our C code, we only reference I and result. Okay, when we write the C code, we do not know what registers will be used. We did not say that R1, R0, and R1. So this R0 and R1 are only visible after you compile the code and you start to translate it into assembly and so on. Okay, when we write the C code, we did not know about R0 and R1. Okay, so as far as the C code is concerned, when I finish the loop, the variable I and the variable result should have the correct values. Okay, but right now, the correct values are inside R0 and R1. Okay, so I need to make sure that these correct values that are in R0 and R1 are updated to I and result. Okay, so that is where the store comes in. So I need to store these values back. Okay, so I need to store this. I need to store this. So this will become modified. Okay, so let me look at the question. Okay, so your processor will execute one instruction at a time. When it fetch the first instruction and it finishes, you'll go ahead to fetch the second instruction and so on. All right, so it's a sequential process, step by step. All right, one instruction at a time. Okay, so we will sort of better appreciate how this works when we are looking at the overall hardware design and architecture. All right, but for now, what you can think of is that it will be done step by step. All right, so every line of code that you see here, okay, every line of code that you see here is executed line by line sequentially. Okay, so of course, if there is a branch, that means it's like a conditional check whether to repeat or not to repeat, then it will not go in sequence, but generally you'll go line by line until the end. Okay, so that is sort of giving you a lower level perspective of how your code is translated, how it sort of works, okay, how you put things together. All right, so in this, we saw a few things. We saw that your memory has both instruction and data. Okay, and there are two keywords that I mentioned just now: load and store. All right, so this is a common keyword that you must always remember and relate to. Whenever we say load, it means from memory to register. Whenever we say store, it is from register to memory. So always remember this convention. Now, whenever we say we are loading from the memory, that means we are taking the data from the memory and storing it or keeping it into my internal register. Whenever I use the word store, it is the other way around. That means I'm storing data means from the register, I'm updating the memory. All right, so these are two keywords you will see quite often. All right, so now let's look a bit more at the registers. So like I said, the registers, you can think of them as just a very small amount of storage space, okay, to hold some information for you. All right, while you are holding on to while you're trying to execute the instructions. Okay, so that is basically what registers are for. Okay, and registers, of course, the number of registers again depends on the processor and the architecture you're dealing with. And registers, okay, the interesting thing is they have no data type. Okay, so it is not like it is an integer or a character or a float. No, a register is just a place to store ones and zeros. That's it. What those ones and zeros mean, again, it all is in the context of the instruction you're going to execute. Okay, so there is no data type associated with registers. It is just a storage space of ones and zeros. When you write the code, we will interpret it accordingly. Now, in the MIPS processor, which we are learning, all right, we have a total of 32 registers. Okay, and the registers are numbered from 0 to 31. Okay, and they are also referred to through a naming convention. So these are the names and the numbers. Okay, generally, okay, in most of our code, okay, we will use the registers from here to here. Okay, so most of our code will make use of these registers plus this register here called the zero register. All right, so we have a zero register, and this zero register is actually a unique register because it only holds a value of 0. Okay, so a register that actually holds a value of 0. Okay, and it's called a zero register. Of course, now you might think, why do I even need such a register? Why can't I just put 0 in my code or something like that? All right. So you will see later why having a zero register can be quite useful and quite helpful. Okay, in many of the coding things that you want to do. All right, the other registers and so on, we won't look at it so much. All right, even though they are there. Okay, so let's have a look at the MIPS assembly language. Okay, so just give me a minute here. Okay, so the MIPS assembly language is written, like I said, line by line, all right, with each line serving a particular purpose. Okay, so even though in C you can write a very complicated line. Okay, so for example, in C code, I can say that X equals to Y plus Z, okay, divided by 100, okay, and this whole thing multiply by 7, something like that. So I can write a very complex statement in C and it is fine. Okay, but as far as assembly is concerned, every line of code is only going to do one action. Okay, it's only one action. All right, and that one action is going to be based on how you interpret the high level code to low level code. All right, so these are some examples of the code. Whenever you want to add comments in the assembly language code, you use the hex sign. Anything after the hex is considered as a comment. Okay, so now let's look at the general instruction syntax. Okay, I say this is general, right? Because again, it will have variations depending on what you're trying to do. Okay, the general form is such where you have 3 registers specified. Okay, out of these 3 registers, 2 are what we call the source registers, and 1 is called the destination register. All right, and the first beginning of the instruction is always what you call the operation. Okay, what do I want to do? Okay, so it's always operation followed by destination, source 1 and source 2. Now, how do I interpret this? So you can see it is add S0, S1, S2. So since S1 is source 1, S2 is source 2, basically what I'm saying is I want to perform an add operation, okay, with the data from S1 and the data from S2, and I want to take that result and put it into my destination register, which is S0. Okay, so that is basically the general syntax. Okay, but we will look at variations of this later on. Okay, so there's a question, if you want to do more complex like 3 addition, you need to split them. Yes. Okay, so as long as you want to do anything more complicated, you need to split them up step by step. Okay, again, like I said, all of this is actually handled very intelligently by the compiler. Okay, so at a high level, we can write whatever we want. The compiler helps us to translate everything into these low level instructions. Okay, so in terms of C, you can relate it to this one line here. Okay, S1 plus S2, put the result into S0. Okay, and that translates into what we see here in this assembly language instruction. Okay, so of course, a question you might ask is, how do I know where or which register it maps to? How can I say that A will map to S0 or B will map to S1 or C will map to S2? Okay, so this mapping of variables to registers, okay, is again handled by the compiler, because at that point of time, okay, when it's compiling the code, it will know which registers are available. Okay, so depending on which registers are available, it will decide to use those that are available and do the translation for us. Okay, when you are writing your own assembly language code, of course, then you can decide and say that, okay, in my code, I will say that S0 is A, S1 is B, and S2 is C, and so on. Okay, so you can do the mapping. Okay, but when you are doing a translation, the compiler will actually do it for us. Okay, how about subtraction? Subtraction is again similar. Okay, you only need to replace with the correct operation. So add or subtract or so on. Okay, but the same idea is there. This is source 1, this is source 2. So I'm going to do a subtraction and put the result into S0. Okay, so this is again the question just now. All right, what if I want to do more complex stuff? Okay, B plus C minus D. Okay, so there is no instruction to do this. All right, so you need to break it down into multiple instructions. Okay, so one way of doing it is something like this, where you can say that I will take b plus c, okay, s1 plus s2, okay, and do the addition first, and then the t0 comes here, and that one I do the subtraction. Okay, so again, if we leave it to the compiler, it will follow and break it down based on the rules that it has. Correct. So if you remember, in C programming, we have the precedence, correct? Operator precedence on which one is more important. So of course, if you put a bracket, then the bracket one will get executed first. If not, it will go based on the order of precedence, okay, that we have in C programming. So that will also translate into how the assembly language will be translated. Okay, so this is another example of something more complex. So in this case, we emphasize the order through the brackets. Okay, so we can do the two addition first, followed by the subtraction. Okay, so you can see that whenever I do an operation, okay, I take the result and put into another variable to hold it temporarily, and then again, okay, hold it temporarily, and then I do the final subtraction after that. Okay, so this is again to show you how it translates, okay, high level code into low level code. Okay, again, these are just other examples, okay, which you can see for yourself. All right, so it is just again, this is very basic stuff, so it's a bit easy to relate. I think the important thing is just understanding the syntax of how MIPS assembly language actually functions. All right, so now let's look at a slight variation to the instruction. So until now, okay, if you look at it, all our instructions, okay, that we have seen so far have three registers involved, okay, where you specify destination register, source 1 and source 2. All right, so that is one way of writing assembly language instructions. Another way is how about performing with what we call a constant value. Okay, constant value is also known as the immediate value. Okay, that means you know upfront that I want to do an operation with a fixed value, a constant value. Okay, so for example, this a is equals to a plus 4. Okay, so this is a C statement. So when I write this statement in C, when I translate it to assembly, what will I see? I will see that it translates to this instruction called add I. So instead of add, it becomes add I. So the I stands for immediate. So in this, you have only two registers. Okay, one is the source register, the immediate value. Okay, you're supposed to do the addition and you're supposed to put it into the destination register here. So this is the immediate value. Okay, so this immediate value, okay, again, a question you might have is, what is the range I can put here? Can I put 1 million, add with 1 million? Can I put add with 10 million? Can I put with negative 10? You know, so what is the range? So the range is specified by this. Okay, why is this the range? Why are we limited by this? Okay, I will answer this question again at a later time when we look at the processor architecture in more detail. But from this, you can, if you remember just now the formula we said, for any 2's complement representation, the range is negative 2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. So from this, you can say one thing very clearly, n minus 1 is equals to 15. So n is equals to 16. That means this is the number of bits for immediate value. That means I'm going to use 16 bits to represent the immediate value over here. Okay, why are we limited by 16 bits? Okay, again, we will have a better understanding of why 16 bits when we look at the hardware. Okay, now this instruction, every instruction is how many bits? Okay, let's go back a bit, to one of the earlier slides. Okay, so the MIPS processor, like I said, has 32 registers. Okay, and each register, okay, each register is 32 bits. Okay, so you have a total of 32 registers, okay, which is numbered from 0 to 31, and each register itself has 32 bits. Okay, so every instruction that we are dealing with, okay, every data we are dealing with is all within 32 bits. Okay, so okay, we will see how we can relate that in a while. So let's come back here. Okay, now, so we look at the add instruction, then we look at the add I instruction. Now let's look at the 0 register. So just now I mentioned that we have a register 0, and basically the register 0 only has a value of 0, nothing else. Okay, so how is this useful? How is that useful is because you have, for example, a C statement like this, where I want to copy the data in G, variable G, to data in variable F. Okay, data in variable G to variable F. Okay, how can I do it in MIPS assembly language? I can say add S1 with 0, because when I add with 0, nothing changes, correct? So whatever is in G will come to F through this instruction. Okay, so of course then it comes to another question: why must I do this in such a funny way? But why can't I just have a copy instruction? Okay, and just do it that way. Why must I do add with 0 and then do this? Okay, so it all comes down to making the instruction set architecture as lean as possible. Okay, so when a processor is created or designed, you want to be able to do, of course, a lot of complex things with it, but at the same time, you want to keep the architecture as simple as possible. Okay, the architecture is simple, that you can, using that basic architecture, you can do a lot of things that is more efficient. Okay, compared to you having a very complex architecture to try and do many different things. Okay, so it is just like for example, you have an oven at home, correct? So you have an oven at home, you can bake a cake, you can bake cookies. Okay, you can do a lot of things with that one oven. All right, so if the oven is versatile, a very simple oven can do a lot of things. Okay, compared to, let's say you have to buy one oven to bake cookies, one oven to bake cake, and so on. All right, then it becomes very complicated. Okay, so the idea is you want to have something that can be reused again and again. Okay, with just some simple modifications. All right, so that's the idea. That means since I already have an add instruction, all right, if I add with 0, I can easily use that approach to copy data from one variable to another variable. Okay, so that really helps to make it simple and not have to add another instruction just specifically for this. Okay, so there is also what we call a pseudo instruction in MIPS, okay, which I will show you in the instruction set in a while. But pseudo instructions are not real instructions. That means they are there to help us make our life easier. So even though you may write this in code, okay, in the end it will still get translated to this. Okay, so pseudo instructions are just like a shortcut technique to make our coding a bit easier, but actually at the hardware level we are still doing it in the add with 0 approach. Okay, so it's not a real instruction. Okay, so next is logical operations. Okay, so just now we were looking at the add and subtract and so on. So those are what you call the arithmetic operations. Now, logical operations are basically to perform the operations like AND, OR, and so on. All right. So in the normal C programming, okay, these are the operators you are probably familiar with. You can do a shift left, shift right, and, or, and not. All right. In the assembly language, you can perform the same thing. All right. So when you do all of this, you have to remember that we are looking at registers as a place to hold ones and zeros. Okay. So we're not looking at it specifically as an integer or a character or anything like that. Okay. So it's just ones and zeros, and I can use these MIPS instructions to perform logical operations on these ones and zeros. Okay. So again, this is just a quick overview of AND gate, OR gate, NOR, and XOR. Okay. So when I do an AND operation, again, as long as any input is 0, the output is 0, and all is 1, the output is 1. If I do a OR operation, only when OR is 0, then the output is 0. As long as any one input is a 1, okay, the output will be a 1. Okay, NOR is basically the opposite. Okay, it's just like OR, but the opposite of it. And exclusive OR basically is simple. As long as the inputs are different and the output is 1. Okay, so if the two inputs 0, 1 or 1, 0, that means the two inputs are different, the output is a 1. If not, the output is a 0. Okay, so let's just look at how some shifting operations can be done, okay, in the MIPS. If I do SLL, that is shift left logical, okay, that means I'm going to shift all the bits to the left. All right, so let's look at this example. So I have a register S0, and I'm going to do a shift of 4 bits. So I say shift 4 bits, what happened? That means this bit over here is going to shift to the left by 4. So 4 means 1, 2, 3, 4. It will come here. Okay, so the 0 will come beside it, 0 and 1. All right, so after I perform this operation, what will happen is this 4 bits here will come to the upper next 4 bits, and everything similarly will get shifted. Okay, so when everything gets shifted, what happens? The upper 4 bits will get shifted out, so it will no longer be part of the answer. But what gets shifted in? Zeros get shifted in. So this is the way in which the shift left logical works. Okay, so when you say shift left logical, I'm shifting all the bits to the left by a certain number of positions. So whatever is on the leftmost will get shifted out. Okay, whatever is on the right will be 0. Okay, so where will shifting be used? Okay, so shifting is an easy way to perform multiplication and addition. Multiplication and division. Okay, so let me explain to you how it works. Okay, take for example, I take this binary value, okay, 0, 1, 1, 0. Okay, so this is value 6 in decimal. Okay, if I take 0, 1, 1, 0 and I say, okay, if I take 0, 1, 1, 0 and I say shift left by 1, then what will happen? This bit will come here, so it will be 0, 1, 1, and this 0 is considered shifted out. Correct? So this is no longer inside, and what gets shifted in is a 0. So I'm just dealing with 4-bit values now. So the most significant bit will get shifted out. Now when I look at this, what is the answer that I get? 1100 is actually 12 in decimal. So what is actually happening is when I shift left by 1, okay, it is equivalent to saying multiply by 2. Okay, because 6 times 2 is 12. Okay, similarly, if I shift right, the same 4-bit value, if I shift right by 1, then what happens? Okay, this one will come here, 0, 1, 1, and this one gets shifted out. So what gets shifted in is 0, and this value is what? 0, 1, 1, 0, 0, 1, 1 is actually 3. Okay, the value 3 in decimal. So when I do a shift right by 1, is equivalent to divide by 2. So 6 divided by 2 is 3. Okay, so that is where shifting actually is very, very helpful. Okay, but of course, this is not the only use case. We will look at other use cases later as well. Okay, but generally, shifting is a very efficient way of performing multiplication and division. Okay. Okay, so actually the answer is here. Okay, multiply and divide by 2 to the power n. All right, so for example, if I have a C statement to do this multiplication, okay, the compiler may interpret it this way. So instead of saying multiply by 8, I say shift left by 3. Okay, so in most cases, a shift left and shift right is always a preferred option compared to multiplication. Why? Basically because multiplication is actually very complex. Okay, it's a very complex operation at the hardware level, which takes a lot of time. Whereas shifting is very, very fast. Okay, so as much as possible, the compiler will try to translate your multiplication and division operations to shifting operations to make it more efficient. Okay, so the next one is the AND operation. So the whole idea of AND is to clear bits, okay, and keep bits. So what do you mean by clear bits and keep bits? Because when I do an AND operation with a 1, I will retain the original value. If I do an AND with 0, it will become 0. Okay, so if you look back over here, okay, if you look at the AND gate, as long as I do an AND with a 1, okay, 1 and 1, the answer will be a 1. As long as any input is a 0, the output will always be a 0. Okay, so the AND is a way of deciding to keep certain bits and clear certain bits. All right, so over here, how we can interpret is this. Okay, the register T1 is what we call the original value. Okay, that means the original 32-bit value. And T2, okay, is actually what we call a mask. Now, what is a mask? When you wear a mask, what are you trying to do? You are trying to show certain parts and hide certain parts. Correct? So the whole idea of a mask is very simple. What you want, okay, what you want to keep is 1. Okay? What you don't want, you put a 0. Okay, so what do I want? I want these 4 bits. Okay, that means for some reason, I'm only interested to know what are the values in these particular 4-bit positions. All right, the rest I'm not interested. Okay, so that is why only these 4 bits I put a 1 and everything else is a 0. So what happens when I do an AND with the 0? What happens? It doesn't matter whether the original T1 value is 1 or 0, because the moment I do an AND with the 0, the answer will always be 0. Okay, so that is why we say what you don't want, you AND with the 0. Okay, now when I AND with a 1, what happens? I will perform the AND operation, and whatever is the result is based on the actual data. That means when I end with this 4 ones here, what will happen? When the 0 end with 1, I get 0. 0 end with 1, I get 0. 1 end with 1, I get 1. 1 end with 1, I get 1. That means you can see that when I end with 1, I'm actually keeping the original bit information. Original bit information is 0011, and that same information is captured in the result. Okay, but everything else, the bits before and the bits after, I did an AND with a 0, so everything else becomes 0. Okay, so that is where the bitwise AND operation is again used for the masking. Okay, so this is of course a very important technique, okay, in programming to focus on specific bits that you want. Okay, so you may have a 8-bit value, 16-bit value, 32-bit value, but you only want to look at a particular bit, okay, to understand whether it is a 1 or a 0. So that is where the bitwise operations come in. Okay, so this is another example. So in this case, I'm only interested in the last 12 bits. So since I'm only interested in the last 12 bits, the last 12 bits are all 1 in the mask. Okay, and everything else is 0. So when I do the AND operation, okay, what will happen is I'm only going to retain the value of the last 12 bits and everything else will become 0. Okay, so in terms of OR operation, it is basically to place a 1 in the result. Okay, so for example, if I say that I want the output bit to be 1, then I OR with 1. If I want output bit to be original value, then I say OR with 0. Okay, so let me show you an example. Now when I do a OR with this, okay, so when I OR with a 1, okay, so if you look back at your OR truth table, when I OR with the 1, the output will automatically become 1. Okay, when I OR with the 0, I will retain the original value, nothing changes. Okay, so if this is my original value over here, this one, and this is the mask, so what will happen is all those values in the bits that are 1, the output will become 1, because when I OR with the 1, the output will always become a 1. But when I OR with the 0, nothing changes. I will retain the original value. Okay, so that is what you see here. All these lower 12 bits automatically become 1, but the original upper bits are all retaining the original value. Okay, so that is the use of the OR operation. So it's two different things. When you use AND, you generally want to clear certain bits. So you clear certain bits by AND with a 0, and you keep certain bits by AND with a 1. Okay, for OR operation is you want to change certain bits to 1, you OR with a 1. Certain bits you want to keep the original, so you OR with the 0. Okay, so that is the use of these two type of operations. The other one is NOT operation, to do a flip. Okay, so there is no NOT operation. All right, but you can do a NOR with a 0. Okay, so this one I will leave it to you to have a look at it and figure out how it works. But if I do a NOR with a 0, is equivalent to doing a NOT operation. Okay, so this one I'll just leave it first. Okay, you can try it out later, okay, or when you're free to understand how this works. Okay, if not, next week I'll explain. All right, again, why do we not have a NOT instruction? Okay, why must we do something so funny like this? Again, it comes down to minimizing the need for additional instructions and hardware if the existing instructions and hardware can actually do it for us. Okay, so that is, it comes down to that. All right, we want to optimize and reduce unnecessary hardware in the system. Okay, so XOR operation is also something you can do. All right. Again, you can perform a NOT operation, okay, by doing an XOR with all ones. Okay, if you do an XOR with 1, okay, your answer will be equivalent to a NOT operation. So again, this is something I would like you to look at it, okay, and try it out first, and then next week I will show you what it means. Okay, and this is last part over here, just to show you how to load a 32-bit value. Okay, I think this part I will leave it first, all right, because I think you will probably appreciate this better when we look at more instructions and why this is significant. Okay, now all these instructions, okay, are inside the instruction set. Okay, I'm not sure if it's ready on Luminous. If it's not, I will upload it, okay, for you to have a look. All right, so there are a lot of instructions that are supported. All right, the instruction set is quite comprehensive, but we will focus more on the basic instructions like what you see here: the addition, subtraction, shifting, and some logical operations. Okay, so we will get more practice over time, and of course, the more you practice, the better you will get at it. All right. So I will upload the full instruction set. Okay, but you don't need to worry about a lot of instructions. Okay, so it's quite lengthy in terms of the whole instruction set, but we're only going to focus on a small subset of it. All right, so you can have a look. All right, again, we are still going to be talking about MIPS, other instruction sets, and then the hardware over the next few weeks. All right, so this whole MIPS chapter, everything is interlinked. All right, this chapter up to everything we're going to do up to week 7 is all linked. Okay, which means that you have to keep up with what we are discussing so that you know what is happening. All right, if you just suddenly start with week 5 or week 6, you will have no idea what we're talking about. Okay, because everything is progressive. Okay, so you need to make sure that you sort of keep up, then you are able to understand what is happening. Okay, so again, this chapter is just to give us a nice introduction and get started with MIPS, and then next week onwards, we will look at more instructions and how to write some assembly language code to get some things done. Okay, so again, those a few things just now that I asked you to look into it, just try it out on your own to see how it works. Okay, and then I'll explain next week. So next week, we will start off with the tutorial first. Okay, which I've uploaded. Okay, and after we finish that tutorial, then we'll continue with the next chapter on the MIPS. Okay, so yeah, that's all we have for today. If you have any questions, you can ask me. If not, thank you and good night. I will see you all next week.